All right, go ahead and get your homework out. Books open to page 491. Books open to page 491, unit number 7, 11, 15, and 19. And we've been working, remember, with the number of possibilities that exist in an uncertain situation. Class, we call this number of possibilities that exist in an uncertain situation.
Probability.
Counting, very simply, right? We talked about multiplication, if values could be repeated, combinations, permutations, and then it seemed like kind of a random thing to insert, except it used combinations in the formula, and we went to something that really might have fit better way back in the day when we were talking about raising to powers, right? And so we looked at raising binomials to powers, and we said that rather than using combinations to raise to powers, it's easier to use Pascal's triangle. And it's based on combinations anyway, but it's less math. So I said, let's just roll with that and do things the easy way. But we did have to use a combination if we wanted to find a specific numbered term of an expanded binomial. And for that, we have the binomial formula. What is that binomial formula? Kendall? Really, really close. You got just about every little piece. There's just one little change. Do you see it yourself? Anybody? NC minus 1. So the same r minus 1 is the power of the b is the same thing here. And technically, this is n minus r minus 1, which is just the difference of these two values. So we were using that specifically on 15 and 19. But number 7, first of all, was just a total expansion. We had an x plus y being raised to the 5th power. And really straightforward, as long as you had Pascal's triangle, and all of you should. What do we start with, though, Audrey?
1, 5, 10, 5, 1.
You just write out the coefficients of the row that begins with the 5. I say begins with the 5 because everything technically begins with 1. So the second number would be kind of my number to look at. Once I've written these coefficients, Brandon.
X to the x equals x cubed, x squared, x gone.
And then, of course, as you did say, x gone at the last term. And then Abby?
Gone, y to the first, y squared, y cubed, y to the fourth, y fifth, y to the fifth.
And then the last thing we need to put in are our signs. Genesis, what do I do here? They're all positives anyway. And so, you know, if you're working at your own speed, in about 30 seconds, you've got this problem completely expanded without doing any math. So I think this is a lot easier than the way the book approaches it. How many had this answer for number 7? Are there any questions on 7? Number 11 was the next one we did. This one not quite as straightforward because there are numbers. There's values built in. Now, I'm still going to start the same way because it's also to the 5th power. That wasn't on purpose, but hey, we can take advantage of it. So we're still going to have the 1, 5, 10, 10, 5, 1. Give myself just a little bit more space here. And this time, though, it's not just an x that we raised to the 5th, Maddie, but a 4x that has to be raised to the 5th power. And then the next term, it's a 4x to the 4th, and so on and so forth. I said for my purposes, though, I don't like writing this and then have to do a lot of calculations later. You could. I'd rather kind of do them as I hit them. So what is 4 to the 5th, Maddie? Good. So for my 1, 5, 10, I'm actually going to spread these out just a little bit more. 10, 5, 1. I'm going to go ahead and put the full 1024x to the 5th. And then for the 4x to the 4th, we'll do... And then when we cube it, certainly don't need a calculator at this point, then... There we go. How many did it this way? You went straight to the expanded number. Anyone start with the powers written? Okay, I think this is more efficient because we also now have to approach the 2. And of course, Michael, the 2 starts out
gone.
But then we have a
2, 4,
2 squared,
8,
2 cubed,
16,
2 to the 4th, and
32.
2 to the 5th. And of course, again, like the last one, all the signs positive. What would we do if we had a negative class? Would they all be negative?
Alternate.
They would alternate, right? We'd start with the understood positive and then alternate negative positive from there. Then it just came down to doing all the multiplication that was needed. And what did we get for our final answer here on number 11, Kendall?
1,024 plus 2,650 is
650 or 560?
650.
Because I got a 5, I got a 2, and a 256. Is that right? It is 256? There should be 10 from the 2 and 5 times 256.
Oh, yeah.
So it should be 2,560. All right, x to the 4th, keep going.
2,560 x squared.
All right, so another one of those numbers, okay?
Plus 1,280 x squared. Plus 320 x. And then plus 30.
How many had this answer for number, whatever it was, number 11? Questions on this. Questions on how to expand when there's numbers in both spots. A little bit more math necessary here. So the first one couldn't have been easier. This one probably takes a minute or two to actually finally work through, and the calculator is certainly a help. Any questions on expanding binomials? Raising them to powers? I just hope the power I ask for doesn't go bigger than your triangle. Abby and Brandon should be just fine on that front. All right, turn the page. Now let's take a look at 15 and 19, where we were finding a specific number of a specific term here. And so using this formula, NCR minus 1 times a to the n minus r plus 1 times b to the r minus 1, we were asked to find, I believe it was the 5th term of x minus y to the 8th, if I am not mistaken. Yes. All right, so the first thing I said I want you to do is identify what is n and what is r. And Abby, what is n and what is r?
N is 8 and r is 5.
How do we know what n is and what r is, Genesis?
What n is the power it's raised to, and r is the term.
Good, it's the term we're finding. So we're going to start off with a combination class, but it's going to be a combination of 8 take 4, r minus 1, remember, so not the actual r. Then we're going to raise the first term, which is all a means, which in this case class is an x, and we're going to raise the x to the n minus r plus 1, or subtract those two numbers. Class? 4. Gives you the same thing. 8 minus 5 is 3 plus 1 is 4, or if you subtract the numbers, you get the 4. And then finally the b. Now be careful. What is the b in this problem, class? Negative y, and that's important, especially if you end up with an odd exponent. But as it turns out, my exponent is the same r minus 1 we have here, so class, to the 4th, the negative would fall off. So you'd be saved basically by the negative, by the even power here. What do we end up with for our answer on number 15? Maddie? Good. How many had 70x to the 4th, y to the 4th? I feel like we did a very similar problem, if not the same problem in our last lesson as well. Number 19 takes on a little bit of a different look here. We want the second term of, and this one we probably could have done without the formula, but I'll show it with the formula anyway. X minus 3y to the 6th. I mean, you're only going 2 terms in. How hard could that be to figure out by the expansion method, right? Like I showed yesterday, and once we got like the 14th term of something, we're like, well, we don't really want to do it that way. We could do it that way, but we could also use the formula. What is n? What is r? Kendall?
N is 6 and r is 2.
All right, so we're going to take a combination class of 6, take 1. My a in this particular instance, Brandon, is x, and it's going to be raised to the 5th power. N minus r, 4 plus 1 is 5, or subtract the numbers. And then my b in this particular instance, Audrey, is good, negative 3y, and it's going to be raised to the r minus 1 power, the same matching number here, so that we end up with just the first power. Well, a negative 3y to the first class, it's negative 3y. So it really comes down to this combination of 6 take 1, and what is that number, class? 6. So we take a 6 times a negative 3 course, we're going to keep the y, and then x to the fifth is just x to the fifth, and we should have had negative 18 x to the fifth y. How many had that answer for the number 15, or 19, excuse me? All right, questions at all on this? Any questions on this? Flip back to page 491 real quick. I want you to do 1, 3, and 9. 1, 3, and 9 on page 491. Page 491, do numbers 1, 3, and 9. Expanding out those binomials. Again, have your Pascal's triangle out and usable. Remember, you can use that as a cover sheet on quizzes and tests so long as you don't write anything else on there except the values of the triangle. Once you finish, check your answers. If you're good, tackle 13. 13's a dilly. Not harder, though. You have a calculator, so it's only big and nasty looking because the numbers are going to wind up big. But you have a calculator to do the work, so 13 shouldn't be bad. But wait till you finished with 1, 3, and 9 and you checked. If you check your answer and you don't have the same answer, raise your hand if you can't figure out where the difference comes from. most of us are working on 13 right now. Anyone still working on 1, 3, or 9? Okay, that's okay. Take your time. Curious to see if anyone gets number 13 perfect. I think we should. Brandon's got an answer. Michael's got an answer. Just a little longer. Pencils down, even if you're not finished with 13, even if you're not finished with 1, 3. Now, go and put your pencils down and take a look at the answers here. Again, the key is don't get ahead of yourself. Take the time to put the 1, 3, 3, 1. Now, if you see a lot of stuff in here, give yourself more room. For instance, here I didn't put a whole lot of room between the 1, the 3, the 3, and the 1 because I didn't have a lot of stuff going on. Here I spread them out a little bit further because I had more stuff happening. Okay, so just a strategy tip there. And then take your x, cubed squared first gone, your y, gone squared first squared cubed, put it on your positives. First one we all should have gotten perfect, is that right? Show of hands. On the next one, this is where with 2 different numbers we had to be careful, but still start with the 1, 3, 3, 1. Then we got the 5x is being cubed, that's 125x cubed, then squared is 25x squared, 5x to the first gone. The 2y is gone, first squared becomes 4y squared, cubed becomes 8y cubed. Put in your alternating signs, positive, negative, positive, negative. Be careful with your multiplication. And should have come up with 125x cubed, negative 150x squared y, positive 60xy squared, negative 8y cubed. How many got every sign, number, and exponent perfect? All right, questions on it. What happened?
I just flipped the signs.
Just flipped, oh, so you had a negative as the very first. So remember, always going to start with the positive and then the alternation happens. Just took that thought away there as well. Did the same thing happen on number 9 by any chance? Okay, so we learn from it, we move on, we're going to be fine. On the last one, very similar approach. We just have the one number here, we plug in the numbers, we work it out. How many got that same answer? 8x cubed, negative 12x squared y, positive 6xy squared, negative y cubed. And again, perfect except the signs were all backwards. Okay, and we're going to get that right next time. Questions on 1, 3, or 9? All right, Brandon, you were the first one done with number 13. What was your answer?
4,096 x to the 4th plus 6,144 x cubed y plus 3,456 x squared y squared plus 864 x y cubed plus 81 y to the 4th.
Outstanding. Anyone else get that same exact answer? Again, for the camera, in case you couldn't hear him, 4,096 x to the 4th, positive 6,144 x cubed y, positive 3,456, that's a cool number, x squared y squared, positive 864 xy cubed, positive 81 y to the 4th. Any questions on 13 from those who attempted it and maybe had a issue? No issues. All right, turn page. Do 17 and 21. 17 and 21. On page 492. 17, 21, and I do have a third one up there on the board. It's not in your book. I just put it up there on the board for you. Pretty good on the first one. You got that really huge, annoying answer. All right. Questions?
No, I just forgot to subtract 1 from the 4 for all of them.
Gotcha. So you would add that. Yeah. Gotcha. Several people got it. A few people still working. Michael got it. Good. Genesis, good to go. Cabby. Excellent. All right, any questions at all on these? Again, they're kind of some algebra topics that got thrown into the middle of possibility scenarios, right? So these really don't have a lot to do with it. It's just the connection of how the combination works in Pascal's triangle. That's really the only reason they're thrown into the middle of this, or toward the end of this chapter. Questions at all on this? All right, well, I want to kind of build off of then that possibilities idea, right? For instance, if we say by counting there's, 2,000 possibilities that exist in a certain situation, then the odds, if you will, or the chances or the likelihood of one specific event happening will be 1 out of 2,000, right? Michael, in fact, used the term probability earlier, and he was a bit early. Counting tells you how many possibilities exist. Probability tells you what is the likelihood that a specific event occurs based on how many opportunities are out there. Does that make sense? And that's what we're going to be talking about now as we transition into chapter 11. So next term in your notes, probability. Probability is the likelihood of an event occurring. The likelihood of an event occurring. Probability, the likelihood of an event occurring. I said a moment ago that if there were 2,000 possibilities that we figured, either by counting, combination, permutation, we figured out there's 2,000 possible ways things could go, then one specific way things could go would be a 1 out of 2,000 chance, or a 1 to 2,000 chance. Notice that probability is most commonly expressed as a ratio. Go ahead and jot that in your notes. Probability is generally expressed as a ratio. It could be expressed as a percent, I suppose, 0.05%, I think, 0.005%, something like that, trying to do it off the top of my head. Very low percent, right? But probability, the likelihood of an event occurring. The equation, if you will, for this, and I'll call it an equation or formula, probability, or P, is basically going to be the number of desired outcomes, over the number of possible outcomes. For instance, all things being equal, there are 16 kids in a PE class. And one of the kids is like, ooh, I hope I get to be captain. Well, you guys who've been in PE know the odds of you being a captain are directly tied to how you perform on the field, right? Somebody is clueless, they're in most cases not going to be a captain. I've had a couple of clueless people made captains because people thought they were being funny until they ended up on their team, and that was sad. But if it were maybe drawn out of the hat instead of chosen by peers, 16 kids in the PE class, and the kid's like, I wonder what my chances are. Well, 1 to 16. We do understand this, though, that not all probabilities are equal, right? For instance, we could say that if I go to a Major League Baseball game, and I'm like, all right, instead of, Freddie Freeman batting, we want Robert Nadasky to bat in his place. I'm going as the pitch hitter. What are the odds I hit the ball? What are the odds I get a hit? Well, pure statistics would say 1 out of 2. Either I do or I don't. Well, let's be real, people. The odds are way lower than that, aren't they? I've never faced a 95-mile-an-hour fastball in my life. I ain't hitting that ball. I'm trying not to get killed, all right? Based on past history, there are certain people in Major League Baseball who, when they step up to the plate, you feel really good about your chances. There are other people on my team as I watch games, I'm like, oh, bases are loaded, but look who's up. This is not going to go well, right? Because we have a past history, right? Past history says this is not going to go well versus this is going to go great. If we have probability based on past history, we call it relative frequency. So write that in your notes now. Relative frequency is probability based on past history. Probability based on past history, as opposed to a blind chance. Now, in some things, past history doesn't matter, right? If I get out a coin and I say, all right, heads or tails, past history has nothing to do with that coin flip, right? But if I'm like, all right, if I shoot a 3 and I make the 3, everybody gets out of school tomorrow. You're probably going to be in school because I was never a great 3-point shooter. The odds are pretty good I'm missing. Now you say, well, it's 50%. Either he makes it or he doesn't. No, we have a past history we could look back at and say, it's not likely he hits the 3. Now, if I take 10 threes and I make one of them, you get out of school tomorrow. That probably could happen, okay? But not one shot, and and plus we wouldn't get out of school anyway. But you get the idea. We slightly can modify our probability formula if we're talking relative frequency by inserting the word successful. The number of successful outcomes versus the number of possible outcomes in the past. So it's not a different formula for relative frequency, because relative frequency really is probability. It's just one is blind chance. For instance, you roll a die. right? Six-sided die. You roll a die. Really, truly, the odds are any one of those 6 numbers could come up. There isn't well-established history, unless they're loaded dice, Michael. Michael has this look at us and says, no, I can make 7s come up every time, Mr. Nadasky. You roll the die, and really, truly, the odds are pretty good. It could be any one of 6 numbers, right? There's not an edge one way or the other. Now, loaded dice. I have a history of 7s come up when I roll my 2 dice, right? And short lifespan in Vegas if you do that. Well, then we would take how many successful outcomes have existed in the past versus how many possible outcomes. For instance, if we've got a guy, you know, we're about, 15, I think 17 games. My Cardinals are 17 games into the baseball season. And if a guy's gone to bat 50 times and he's only hit the ball 5 times, it's not a 1 out of 2 chance he's hitting the ball. Based on his past history, 5 out of 50, there's a 1 in 10 chance he's getting a hit. I'm not feeling too good, right? But if it's Nolan Arenado, and his likelihood much higher than that, because he's shown that he can hit the ball more often. Do we see probability, both in the sense of just raw probability, really, truly, the odds are all the same, versus relative frequency? For instance, if you had to reach into a candy jar and all the candies were wrapped the same way, if you didn't look and you pulled something out, that would be probability. But if you got to look in there and choose what you wanted because they weren't all wrapped the same, think food drive, right? That's relative frequency. Relative frequency says most kids want these, not those, right? And there's this one candy that's always at the bottom of the bag because nobody wants it. All right, questions on that? Look at page 495 now, and I've got a couple of examples here. The first one is a true probability. I'm going to read example 11.1a for us, if you would, Audrey.
8 marbles are hidden in a bag. 4 marbles are red, 3 are blue, and 1 is yellow. What is the probability for anyone selecting a blue marble?
Again, if someone's able to look in the bag, that changes things, because now you have personal preference. But if they can't look, it's just reach in and pull one out, that's truly random. So this is a true probability problem. Notice the way in which they describe it. P, and then in parentheses, blue. The probability of blue is, well, how many desired outcomes are there? How many of the marbles do we want? Well, there's 3 blue ones. So there are 3 that I would want to pull out. Make sense? How many total are in the bag, though? 8. So it's 3 to 8. You could say 37.5%. They left it as a decimal. I generally do either percent or ratio. So for our purposes, we would not leave the decimal. I'm a 3 out of 8 guy. It's less math. Don't have to pull the calculator out. Questions on example 11.1a. How many remember this from junior high? All right, should. It's pretty basic. Example 11.1b is a relative frequency problem. We'll go and read the example problem here for us, if you would, Michael.
Throughout the first 4 months of the baseball season, Joshua has 110 base hits out of 345 at-bats. For this data, what is Joshua's probability of getting a base hit when he comes to bat?
All right. And then they have the customary for batting averages to be rounded 3 decimal places. So we take the 110 base hits he's had successfully, divided by 345 chances he's had when he's come to the plate. And when we divide, it comes out to a 31.9% chance. However, yeah, baseball batting averages are decimals with 3 decimal places, so 319. Now, actually for baseball, that's really good. 319 batting average is really strong in baseball. It doesn't sound like a lot to those of us, but I mean, again, imagine hitting a 95-mile-an-hour fastball and it not being caught or you not being thrown out. That's what a base hit would be. Do we see the difference between probability and relative frequency? Again, the book doesn't make the delineation clear. I want to make sure I cleared that up for you. All right. Now, a couple rules of probability in your notes. Rules of probability. First of all, you can never have a probability lower than 0. Can't have a probability lower than 0. For instance, if Brandon, we'll take a purely hypothetical situation. If Brandon's like, I really, really want to ask Abby out. What are the odds of her dad saying I could? I'm making it up, okay? And taking something crazy. All right? What are the odds of her dad saying I could ask her out? Now, Abby would say the odds are 0. Her dad would say the odds are lower than 0. But technically, it can't be worse than 0. The worst odds he could possibly have is a 0% chance. Does that make sense? You can't have worse than that. On the flip side, you can't have a probability over 1 or over 100%, right? An 8 out of 8 chance is as high as you can get, right? You can't have a 9 out of 8 chance or a 120% chance of something happening. So if Brandon's like, I wonder if I asked Abby out what the odds are of getting my face slapped. Abby might say there's a 150% chance of that happening, but she's wrong. There's a 100% chance. They don't actually hate each other. Do you hate each other?
Yes.
They do. Okay, they hate each other. Okay, for the record. In Christian love, of course, but they hate each other. All right, so that's why I picked on them. But anyway, but the probability is always between 0 and 1. So here's the way we'll express it. The probability of some event A always lies, now remember this interval notation? With brackets between 0 and 1. Bracket on the 0 because you could have a 0% chance, and on the 1 because you could have a 1% or 100% chance, which again is a value 7 out of 7, 6 out of 6 just becomes a 1. The other thing though is if there were multiple possibilities that would exist. For instance, we had the possibility of the marbles or whatever reaching in trying to get a blue marble out. Well, the possibility of a blue marble, I think there were 3 out of 8, right? So there's a 3 to 8 chance you get a blue marble. There was 1 yellow marble. Well, that's a 1 to 8 chance. And then there were 4 red marbles or something like that. The overall, the other color, I think it was red, at 4 out of 8 chance. Well, if you add each of the probabilities together, total in a situation, that has to always equal 1. So we would say, remember this sigma notation? The sum of all the probabilities of A sub I, written here with the argument notation, but the sum of all probabilities in a situation always equals 1. Or 100%, you could say. The probabilities have to add up to exactly 1, or have to add up to 100%. So if you look at the example problem, they're on page 496 now. Example problem 496. It lists some probabilities. Now, they didn't do ratios. They did decimals because they're weird. They said there's a 2 out of 10 chance, a 5 out of 10 chance, and a 3 out of 10 chance. Are these a valid group of probabilities? Well, first of all, are any of them smaller than 0, negative, or any bigger than 1? Nope. Do they all add up to 1? 0.2 plus 0.5 plus 0.3, yeah, 1.0. So because they all add up to 1, and because none of them are bigger than 1 or smaller than 0, that's a valid group of probabilities. Look at the next set. 2 out of 5 chance, 3 out of 5 chance, 6 out of 5 chance. Well, even as I read it, you realize one of them screams at you. No, you can't have a 6 out of 5 chance. The probability that they tried to list was greater than 1. You can't have that. No, that is not a valid list. Besides, they add up to an 11 out of 5 chance, which is also not equal to 1. So no, you couldn't have that as a set of probabilities. Questions on those rules of probability? Okay, they should be really common sense to you. Does everyone feel like you understand that? Okay. All right. Next term, you see it there in bold. Oh, there's one more example, top page 497. I felt like I was forgetting something. The next set of probabilities. They have negative 0.3 at the top of page 497. At the top of page 497, they have a negative 0.3. Well, right there. Is that a valid set of probabilities? Not if there's a negative chance. Despite what Abby's dad says, negative chance does not actually exist. The lowest it could be is 0, 0.8 and 0.5. They do add up to 1, but you can't have a negative probability. By the way, do you notice in the little, maybe your book is corrected, my book under number 1 says, check that all the individual probabilities are between 0 and 1. And it says, ask little arrow thingies, the first probability is less than 1. It should say is less than 0. Do you see where I'm at right here? Yeah, I changed it in my book. Change that in your book if you would. Should be that the issue is that the first probability is less than 0. All probabilities have to be less than 1, or at least they have to add up to 1. So the real issue is that the probability is less than 0. Change that in your book. Make that little edit. You don't write in your book. The next person to use your book will thank you. The first probability is less than 0. Or just make a mental note of it. If you have a compulsion of writing in your textbook, that's fine as well. All right, now there are, of course, this idea of things not happening. I think of this as a PE teacher, especially with one of my students who fervently prays for rain just about every day of PE class. And one of my students is laughing especially hard because it's her sister. We will leave culprits nameless for posterity. But this student prays for rain, and unfortunately, she was successful earlier in the year of the Lord answering her prayers at inopportune times. So lately, I've decided to start praying that it will rain, okay, or will not. Excuse me, she's praying it will rain. I pray that it will not rain. I pray that it will be sunny and we can have PE class outside where it's nice and sunny and warm and we all feel good. And so, but she prays, Lord, help it rain. Okay, well, what's the chances that it rains? Well, let's just look at the rain chance and suppose she sees the rain chance is 40%. That's the probability, according to the weatherman, based on all kinds of different data he looks at, the probability of rain. I want to look at this as the probability it does not rain. Well, the probability that it does not rain, class, would have to be 60% chance. If it's a 40% chance of rain, then the opposite would be the difference that would add up to 1, correct? Because either it will or it won't, right? We call this the complement. Go and note that term in your notes. It's in your book as well, but I want you to jot it in your notes. The complement is the probability that something does not occur. The probability that something does not occur. The probability she does not say no. Yeah, well, anyway, good luck with that. The probability that something does not happen. Here's the way it would be notated, by the way. Instead of writing not rain, because mathematicians are lazy. By the way, do you see complement, complete? It completes the full 1. So the complement, instead of writing not rain, because mathematicians are lazy, they'll put a little c, like an exponent. It doesn't mean the c power, but this is the complementary probability of rain. The probability it doesn't rain would be 60%. Here's our formula. The probability of the complement of A, or the probability that A doesn't happen, is equal to 1 minus the probability of A. 1 minus the probability of A. We just take 100%, or 1, and subtract the probability that something does happen, and that gives us the probability that something does not happen. If you would put this on the formula page as well, as complementary or complement probability. Complement probability. Keeping all these formulas together. Yes, sir.
Probability formula.
Did I not tell you to put this on the formula page? Sorry, put that on the formula page. It's in my notes to tell you to do that. And I was, even as I was saying, I'm like, did I remember to tell him that? Yeah, if you'll put this probability formula on your formula page and the probability of the complement on the formula page as well. Just keeping all the formulas together.
So that's the relative one?
This is, well, with these notes, it's relative frequency. With the original writing, it's probability. You just do probability slash relative frequency and kind of put them in there together as one. Good question. So putting the probability formula in, which I should have told you to do about 20 minutes ago. Number of desired outcomes over number of possible outcomes. Or if it's relative frequency, successful outcomes over total outcomes in the past. And then the complement is simply 1 minus the probability of something actually happening. The probability I pass is 1 minus the probability that I fail. Or the probability that I do not pass is 1 minus the probability that I do. Not that we want the probability of not passing, that would be sad. The probability I get an A. The probability I win the lottery is 1 minus the probability, is 1 minus the probability you don't, I guess, anyway. Complement is for those negative situations, the probability something doesn't happen. The odds of not winning the lottery very high, actually. If you do, you'll suddenly find you have lots of temporary friends. A la prodigal son. Yeah. My daughter's got a field trip tomorrow at the zoo. She's like, ooh, Daddy, can I have some money to get some food for the giraffes? I said, well, baby, here's what's going to happen. If I give you money to buy giraffe food, and you buy giraffe food, all your friends are going to come and be like, ooh, can I have some? Can I have some? Can I have some? And because you're a sweet little girl, you're going to give them that food. And you're not going to have much left for yourself. And you're not going to be able to feed the giraffe very much. And you'll be like, I spent all my money on this and everybody else is feeding the giraffe. And they're going to start to resent your friends in that sense. So let's not do that. This is human nature, right? Anyway, do we have these on the formula page yet? I talked long enough to give you time. All right, look at the page 497 at the bottom, the examples. Find the complement of each event. Well, the probability of some event A, they say, is 0.2. So the complement of A, or the probability that A doesn't happen, is 0.8. Easy enough? Look at the next one. Probability that A happens is 2 out of 7. Okay, so the complement is going to be 1 minus 2 out of 7, which is 5 out of 7. Does that seem pretty easy? And they finally give you an actual problem for letter C. Read it, Kendall. The complement of purple. Well, purple is 8 out of 19 total, right? So purple, probability of purple, you see P, and then parentheses purple, is 8 to 19. So the complement of purple, which normally would be written P with purple, if you could spell it, complement, the complement of purple would be 1 minus 8 out of 19. What's 1 minus 8 out of 19? All the rest of them out of 19, right? 11 out of 19. There's an 11 out of 19 chance you don't get purple. So, and that makes Genesis sad. Questions on that? All right, almost done. Next thing in your notes, compound probability. Compound probability. Because a lot of times, let's be honest, as we look at probabilities, we want to expand our chances of something happening. For instance, when we've got, in a baseball game, we got runners on base, I would love a home run, right? But really, a double's pretty good too. I mean, for that matter, even a base hit. I'll even take a walk. And the more possibilities that I acknowledge make me happy, the more likely I am to be happy. And then he strikes out on that. Okay? But to put probabilities together, for instance, we go back to the marbles or whatever that Audrey was reading. We had 3 blues, a yellow, and 4 reds, right? Well, what if I was like, well, I don't necessarily want a blue. Blue would make me happy, but I'd also like yellow. Either of those. I just don't want red, right? Well, in that case, what we could do is we could take the 3 out of 8 chance of blue and the 1 out of 8 chance of yellow. If we add them together, that's 4 desired outcomes. Blue, 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 or yellow, all of them work out of 8, right? So compound probability is anytime you have a probability joined by the word or. Probability, I can't spell. Probability joined by the word or. And in that case, the probability of either A or B happening is equal to the probability of A plus the probability of B. You literally just add the probabilities together. So like, I really want a home run. Well, past history says there's a very small chance that happens. Okay, how about a double? A slightly bigger chance of that happening. Well, if I say either one is good, then I can add those 2 probabilities together, and that increases my chances. Like if you roll a die. And how many play board games that involve dice, you know, moving around the board, and there's this one spot you don't want to land on, but there's this other spot you really want to land on, but this other spot's okay, like Monopoly, and like, how many play Monopoly? Okay, you know what I'm talking about. And somebody's got Boardwalk and Park Place, and they got hotels, and you flew down there, the game is over, and you lose, and you hate losing because you're competitive. And you're like, all right, I definitely don't want to land on Boardwalk. I definitely don't want to land on Park Place. I really want to jump in and land on Go, right? I really want whatever number puts me on Go, because then I'm in the clear for a while. If necessary, the chance right before Park Place isn't the end of the world either, because it'll probably send me somewhere other than Boardwalk, except there is that one card that says advance to Boardwalk, and that's sad. I'll be upstairs in just a minute. So you're like, oh, either this or this. Well, the odds of rolling that Go number plus the odds of the chance number gives you your total probability. If the 2 numbers are mutually exclusive. If the values are what are called mutually exclusive. We're going to talk a little bit more about, well, a lot more about this tomorrow. Mutually exclusive has the idea of if you roll 1, you are not rolling the other. A 7 is not the same as a 10, right? So you're like, I really want a 10. Come on, 10. And it's a 7. Like, yes, I got my 10. No, that's a 7. It's the same thing. No, it's not. Okay, they're 2 separate things, right? But there are instances in which might not be. For instance, in billiards, a black ball or the 8 ball. Well, there are 2 balls with black, 1 stripe, 1 solid. The 8 ball happens to be one of the black balls. Those aren't mutually exclusive. We'll talk more about that tomorrow. Your homework, however, has nothing whatsoever to do with this. Okay, we're going to be picking this up more tomorrow. Homework is to do pages 491 to 492. Pages 491 to 492. Numbers 2, 4, 8, 16, and 18. Page 491 and 492, numbers 2, 4, 8, 16, and 18. And on page 204, a little bit of past review here, keeping our skills sharp for the quarter. Page 204, the review, 5 through 12. Page 204, the review, 5 through 12. All right, we'll take a look at all of this in our next lesson. Have a wonderful rest of your day, and you are dismissed.